Good morning, everyone. My name's Guy Davidson. I'm going to be talking to you about SG14. Also talking today will be Sean Middleditch and Michael Wong. They'll be presenting the second and third parts of the talk. Nick Guillemot also helped us with this presentation. So here's our summary. The talk's divided into four parts. The first part is a brief reminder about what SG14 actually is and some of the problems that typical contributors face in their programming lives. I'll then move on to what's happening at the moment and discuss some papers that are in flight. And this is the meat of the presentation. Sean will be taking over here as well. SG14 is actually having a meeting on Wednesday, so we'll advise you of the agenda. At the moment, most of our contributors are from the games industry, but we are reaching out further into other domains, and we'll discuss some of these. And finally, of course, there'll be the call to action. Really, I suppose the purpose of this talk is to get more people to get involved with our study group, but also with any study group, with the whole of the standardization process. I'll be signposting other talks as we go on, as will Sean and will Michael. If you want to get your phone out and consider your schedule on shed.org, now is the time to do that, and now is the time to fiddle with your device. This is the only time to fiddle with your device. Please make sure your phones are on silent, and be aware of where the emergency exits are. So the group was created in response to a question asked at CppCon 2014 of all of the podium, and that's where are the games company representatives. We have particular needs, low latency, real-time operation, but don't we all, really? Don't we all want to write performant code that runs like a train, that's super fast, super efficient? But we have special needs, particularly in console games programming. Performance and efficiency for games is really important. I work for a games company. So do the majority of our contributors. And I'm going to focus on that domain particularly. But it is quite transferable. Indeed, the interests of all of these areas are served by the group. So the financial side of WG21-SG14, we'll get used to that name. Carl Cook, Neil Horlock, Thomas Rogers, Nevin Liebers, all have a financial interest. And when I say financial interest, I don't mean they're investing money. I mean they're part of the financial. Oh, if only we had people giving us money. There was a talk at 3Stack from the financial software, which is a financial software conference for high-frequency traders, as well as algorithm designers and low-latency infrastructure. We had an SG14 meeting at the major financial centres. Additional notables, of course. The Embedded Programming Study Group was led by Daniel Gutz, and we've taken that on so that there's no duplication. EA-STL is an important library. This was open sourced. Thank you, EA and Rob Powlin. This was open sourced recently and forms many. The library forms many classes that we could consider for use in games. See that paper by Michael Wong, I believe. Now, this is the organization at the moment. Is everyone familiar with this chart? Get familiar with this chart. It's really handy. It's from the isocpp.org website. This gives you the organization. Now, I'm interested in all of these study groups, actually. 1 and 6 have some crossover with us, so that's the Concurrency group and the Numerics group. The Concurrency group, well, everyone's interested in concurrency. There's no end to it. And numerics is actually surprisingly important, as I'll be discussing a particular numerics paper as we go on. So this is how we do business. There's a reflector, a Google group that we send all our posts to, that we discuss in common. It's a really good group, if only because the signal-to-noise ratio is very, very high. There's about 10 posts a day. We don't go shouting at each other. There's no Hitler references, none of that. It's a really very valuable, a great example of good communication amongst experts. There are several papers in flight, and this is what we'll discuss and we put together. There's a GitHub repository, which is not as busy as it used to be, but that's where we'll stage a lot of the papers and a lot of the consideration. We have monthly telecons, teleconferences. They have a good attendance. There's usually over a dozen people. Sometimes we have had over 20 people. So we have to be quite disciplined about taking our turn speaking and getting things together. But we're good at that. We're all professionals. It's chaired by our convener, Michael Wong, who will be speaking with us later. This man is a powerhouse, but I'm not going to embarrass him right now. But we're really very lucky to have him running the show for us. He has interests in many relevant areas, particularly parallelism, concurrency. Now, I was going to show you this trailer, but that would require YouTube and streaming and things like that, so I decided against it. Does anyone here actually play games? Yes, brilliant. That makes life so much easier, fabulous. So that was about 2/3 of the hands went up. Now, particularly, I work on the Total War franchise and the Warhammer title in that franchise. When we had Scott Myers in recently for some training a couple of years ago, and as soon as he came through the door, we started the conversation. And I said, by the way, Scott, we do things a little differently here. And he said, everyone says that, but it's actually true for us. We do things a little bit differently. If you've played one of our games, or if you've seen any kind of simulation, of game simulation, you'll have seen 20,000 figures marching using different animations across the terrain, fighting each other, throwing things. You'll have seen horses or flying creatures, or all sorts of things. But we do this at 30 hertz. It's going through a television screen. Quite often it'll be at 60 hertz, which is very painful, but particularly, we have an awful lot to do in 33 milliseconds. We've got to do all of the activity and all of the rendering. So let's do the maths. On a 3 gigahertz processor, you have 100 million cycles per frame. With 20,000 soldiers, for example, that's 5,000 cycles per soldier. They have to choose what to do and how to animate the soldier as a result of that choice. And then you've got to worry about cache coherency. It's really important to get things done speedily. There are some tricks you can do, which is you can run the world at 10 hertz, not 30 hertz, and then just interpolate the animation. And that gives us 15,000 cycles per soldier instead of 5,000. You can demand two cores of the user and share out some of the work. But of course, we've got to render the output as well, so we end up putting that on a particular core. Fortunately, we have a GPU to help us out. Telling it what to do is very CPU intensive, let alone the actual doing of it. So although it's great, we've got heterogeneous computing, we've actually got to prime the thing in the first place, and it's not a trivial job at all. You have to work out what you have to draw from the camera position, what resources you need to push onto this graphics card, onto the GPU. And we have two different styles of programming for two different types of microprocessor. I say microprocessors, is it nanoprocessor now? They're really tiny. These parts are getting just smaller and smaller all the time. And I haven't even mentioned sound, actually making the thing be heard. And that's not it. There's a variety of specs that we have to worry about. Do we have 64 gig of RAM or 3 gigabytes of RAM? Have we got a £400 graphic card or an integrated laptop part? Which is not great for games, it has to be said. Optimization is front and center. We have to keep the caches full. We have to keep the cores busy. And this is not much different from the regular advice, but we can't throw more cores at the problem. Our software needs to run on a broad set of hardware which is specified by the public, or it's a single piece of hardware which is specified by the console manufacturer. But we don't get a say in what the final hardware is going to be. It's what our customers say it's going to be. We have one fortunate situation, which is that the architectures are all very, very similar nowadays. Since the PS4 and the Xbox One came out, everyone's working on x86-64 processors. They're actually custom AMD parts in the consoles, or an NVIDIA or an ATI or an Intel graphics part. The whole thing is quite different from a windowed application, which waits on messages and then processes those messages and then waits for another message. And it takes as long as it takes to process a message. And if it's too long for you, then you upgrade your hardware and you throw a faster processor in there. That's just not a luxury we have. I just have to keep reinforcing this. We're stuck with what our target market says we're stuck with. SG14 also does cater for embedded programmers. Similar situations with consoles, finite amount of RAM, limited tools. It's a similar experience. Now, I've divided the areas of concern into 6 chunks. So we have fixed point numbers, containers, graphics, concurrency, executors, RCU, which you'll find out what that's for, and hazard pointers, heterogeneous computing. Michael Wong's going to be talking about that. Vectorization and parallelism, and miscellaneous. I'm sorry, miscellaneous is a very weak word to use, but it does reflect the diversity of approaches that we have in the study group that we're bringing to the domain. So, before we go on, does anyone here remember what was significant about the Intel 486DX processor? Coprocessor, yes, particularly. Sorry?
There was a bug in the first processor.
There may well have been, I don't know. But particularly, it was the first processor to come with a mass coprocessor actually on the chip. Beforehand, you had to have another coprocessor. You couldn't rely on it being there. And it was the first Intel processor to ship with a floating point coprocessor as standard. But why are we talking about fixed point numbers? Now, unless you've got a background in mathematics or experience with older CPUs, you probably take non-integer arithmetic for granted, which is not necessarily a bad thing. Who's heard of IEEE 754? Oh, all right, plenty of you. I guess I should have expected that. Right, so plenty of you have heard of IEEE 754. This is the standard for non-integer arithmetic. It celebrated its 30th birthday last year. 30 years old. And standards are meant to be invisible. That's the point of them. They simply state the way that things are, and we quietly, are happy they're there, but ignore them. Not all standards are like that. This one is. And we've got three papers in flight related to fixed point arithmetic. Okay. Take the numbers down, and let's look at why we need them. So, the standard uses two formats offered by IEEE 754, and it adds a third, which is not standard. Binary 32 and binary 64 corresponds to float and double. Long double is typically an 80-bit type, and it's a great mature piece of work. The standard has been optimized to hell and back in silicon for many years now. It's comparable speed to integer arithmetic. It's sometimes it's even faster, occasionally slower. Division, obviously, is quite complicated. But there are two problems with floating point. Uneven point distribution. That's kind of the biggest problem where we're concerned. So consider the representation of a float. As operations are carried out, it grows and reduces. The exponent can get bigger and smaller. The fraction will change, obviously, all the time. But the fact that the exponent grows and reduces implies that what we have is a dynamic radix point, the point where we actually say, here's the integer part, here's the fraction part. And this is why it's called a floating point. But this can represent a vast chunk of the rational number line, but it's at the cost of precision. It looks a little bit like this. You'll get lots of good numbers, lots of precision around 0, and the precision will tail off around the ends, around the edges. You actually have 5 decimal orders of magnitude, so 10 kilometers can resolve reasonably to about 1 meter, 1 part in 10,000. This is a problem. For example, in our battle games, everything has a position. A joint in a skeleton, for example. There's one joint, there's another joint, there's another joint. They're rather less than a meter apart. You could move to double precision, but that would mean doubling the size of your data, which is absolutely not an appetizing thought. As I said, we're constrained very much on the amount of RAM we have. On a large battlefield, you've got fists landing on faces. You've got blades missing by centimeters, narrow escape kind of stuff. And you might decide that you could just not fight at the edges and restrict combat to the center of the battlefield where the precision is nice and high, because that's the only place that higher precision is required, is where the combat is. You actually can't do that. Your designers will look at you as if you've grown another head. They'll say no, straight away. So we're stuck. One solution is to decide that rather than have an uneven distribution of positions over a huge range, you have a fixed resolution over a smaller range. And that's the motivation behind fixed point arithmetic. So John McFarlane, who used to work for Creative Assembly, which is where I work at the moment, and Lawrence Crowell are working on this. SG6, that's the Numerics group, is also looking at this work. It's a more appropriate group, obviously, Numerics, you see. But SG14 is user-focused rather than feature-focused. So there's a potential for a lot of crossover. And we're cooperating with SG1 on concurrency as well in the same kind of way. The fixed point types are actually a library extension. They consist of class and function templates, 2 of which are appended to the type traits header. And the remainder live in a new header file called fixed points. Let's take a look. So fixed point numbers are specializations of this template. So we have a first parameter which describes the capacity and the signedness of the underlying type, which represents the value, which defaults to integer. And the second parameter is equivalent to the exponent, and it shifts the stored value by the requisite number of bits necessary to produce the desired range. The default for this is 0. We also got two helper types. The helper types offer a more intuitive description, I think you'll agree, by using the cardinal number of integer and fractional digits. And we have an unsigned version as well. And this would probably be the most widely seen way of representing, of distinguishing fixed point types. So here's an example, pi, our favorite. Pi is a 32-bit signed fixed point number. So we have two integer digits to represent 3, and which leaves us with 29 fractional digits. So fixed point numbers can be explicitly converted to and from arithmetic types. Significant digits are not lost, but rounding errors will be made. So this equates to true. It's an acceptable rounding error. You've said it's acceptable because you've chosen 4 and 4 for your integer and fractional parts. So operator overloaders are provided. They perform as little runtime computation as practically possible. And with the exception of shift and comparison operations, binary operators can take any combination of 1 or 2 fixed point arguments and 0 or 1 arguments of any arithmetic type. So for example, when non-identical, when you've got one fixed point type and one other type, then we have to apply promotion-like rules to determine the return type. So when both arguments are fixed point, then the fixed type, the result type is the size of the larger type. It's signed if either input is signed and has the maximum integer bits of the two inputs. If one argument is a floating point type, then the result type is the smallest floating point type of equal or greater size than the inputs. And if one argument is an integral type, then the result type is the other fixed point type. So for example, we are adding two different types of two different fixed point types. So that gives us the 5 for the number of integer bits and 3 for the number of fractional bits. If we add an integer to ufixed, it stays as a ufixed 5.3. If we add a float, the type is converted to a float. Now, overflow and underflow.
Some of these are in flux.
They are in flux. I should point out John McFarlane is actually right here in front of me, which makes this a very hard presentation to make.
No idea how much detail you were going into.
Oh, I see. Okay. Thanks for coming, John. Right. Overflow and underflow need to be taken into consideration. Right. Consider this. The result is 16. But this can't be represented with 4 integer bits. We have an overflow. The result depends on how the representation type handles overflow. For built-in sign types, the result is undefined. For unsigned types, the value wraps round. And that's overflow. We're used to it from normal integer maths. But underflow requires a little bit more getting your head around. So look at this. The result is 7.5, 7.5 to be precise. 7 can be represented with 6 bits. 0.5 can be represented with 1 bit, so we have an accurate result. But in the next one, if we're only using 7 integer bits and no fractional bits, we have underflow. We have an inaccurate result. We suffer a loss of precision, but that's generally considered acceptable. When all bits are lost due to underflow, the value is said to have been flushed. And like overflow, the result of a flush depends on the underlying representation. And in the case of built-in integral types, the value will become 0. Dealing with errors resulting from overflow and flush are the biggest headaches in the domain, I think. Integers are easier to deal with. They've got no fractional bits. It's easy. But floating point values are shielded from the problem by their variable exponent. So as the exponent gets larger and smaller, it absorbs all these kinds of errors. The paper presents 4 strategies, which is leave it to the user, promote the result, adjust the exponent, and then this preserves the most significant digits at the cost of the least significant digits. For arithmetic operators, choice 1 most closely follows built-in behavior. It causes the least surprises, and it requires less computation. whereas 3 and 4 represent different trade-offs, neither of which is the best fit in all situations. Particularly, this construct may fail. So choices 3 and 4, promoting the results and adjusting the exponent upwards. They're named functions, so that you know exactly what it is you're doing. You're making that choice. So the function template promote returns the same value, represented by a larger fixed point specialization. So that's equivalent to this. Promoting make fixed 5.2 up to doubling the size will give you a make fixed of 11.4. We've gone from 8 bits to 16 bits. And there's a complementary function demote, which reverses the process. So finally, we've got some named arithmetic functions. We've got some unary functions with these kinds of names, binary functions with these kinds of names. And the paper goes into considerable more detail, which I'm sure John will be talking about later this afternoon. We had some feedback from GDC, but it looks like it's going to go into the language. I'm quite pleased about this. An additional solution, of course, might be to bypass SI units entirely. The problem we have here is we're working with meters and we need to get down to a small resolution. One thing you could do is decide, right, I'm going to work in millimeters. 32 bits in millimeters will give you millimeter resolution from Yemen to Greenland. So if your map is taking place over a big chunk of the world, it's probably quite sufficient. Right, there's one more paper, numeric width. This is paper P0381. It contains a proposal to address manipulating the width of numeric types. It defines these 3 symbols. So which solves an interesting problem. The user must ensure the capacity meets demand. So we're taking 2 32-bit integers, we're multiplying them together, so that means we need to return or accommodate 64 bits. What happens if you've templated that function? What's your result type going to be? Ooh, bit stuck. So we actually have this beast. But our result type is now derived from our understanding of the operand type. Right, let's move on to containers. That's fixed point numbers. So this area probably causes the most heated discussion within our particular community. Containers, people bitch about containers all the time. There are 3 papers in flight, and there's one waiting to launch. There's rings, there's flat containers, there's extending memory management tools. Actually, it does relate to containers. And then there's the colony and stack. Oh, by the way, John, your talk's today at 2 o'clock. John McFarlane, 2 o'clock. For more information on fixed point. Right, the ring paper. So this was proposed last year. It's been through a couple of meetings. It's acquired suggestions for modification. It's acquired a co-author. It's been quite busy. Let me take you back to the 80s. 80s, what do you remember about, who remembers the 80s? Good, lovely. Airbrushes, Athena posters. Programming the Z80 by Rodney Sachs. I read that in the 80s. Great text. Everyone should read it. I first wrote C in the mid-80s. I'd learned BASIC, Z80, 68,000. I thought I'd try another language. Didn't quite realize what I was getting myself into, frankly, but here I am now. It felt like assembly, but with better names for things. It was like a macro assembly language. Now, I took great pride in getting buffers to bow to my command. Particularly what would happen was using DMA transfer, using direct memory transfer. I'd fill up a buffer and then start processing at one end. And then once I'd kind of got most of the way through, I'd start filling the buffer up at the other end. Things would go round and round. I'd have 2 processes working at once. I'd feel like a god. We've all done it. We've all had that moment of supreme potency, thinking, yes, I have 2 things going on at once. This is concurrency. Quick phone Bjarne. This is brilliant. I'm glad it's not just me. But I came across this concept time and time again over the next 30 years, filling something up, processing it, and then filling it up whilst I'm processing it. But everyone had their own name for it, usually 2 words. The first word was something like ring, or cyclic, or fixed, or rolling. And the second word was buffer, or queue, or FIFO. So I'd have a cyclic FIFO, or a fixed FIFO, or a rolling buffer, or a ring queue, or something like that. People are very vocal about identifiers. It's very hard to label things. Anyone heard of Parkinson's law of triviality? So Parkinson, in 1957, he argued that organizations give disproportionate weights to trivial issues. It's also known as bike shedding. Yes, you've heard of bike shedding, the bike shed effect, or the bicycle shed example. And when I first heard of it being used as a verb, I I was a little worried about what lay ahead, because I first heard about it on the reflector. I thought, well, blimey, are we going to be shouting about names? As it turns out, it's all been quiet so far. Now, the ring buffer is a useful container for SG14. It crops up everywhere. The usual uses are for asynchronous processing of messages or for keeping a buffer of the last n events. It differs from std_q. That's an adapter of list or deck, but it's not necessarily contiguous. It's in progress. I'm hoping to have it in for C++20. Has anyone submitted a paper to the standards body in here? Okay, great, excellent. So my story is that I started work after ACCU 2015, which was in England. That was about the spring. And I thought it was finished after about 3 months of tinkering and some review from friends and colleagues. After all, it's not a tricky concept. How hard can it be, really? I posted it to the reflector for consideration. Then I first presented it at CppCon this time last year. Got some feedback, spruced it up. Michael Wong presented it at Kona in Hawaii in 2015. It got a bit of a lukewarm reception. There was some very matter-of-fact note-taking, which was a good thing, frankly. My implementation of POP was unpopular, and it was decided not worth putting in the standard. Maybe if it was a circular range, that'd be good. What if you didn't own the memory? Or if you supported iteration? Maybe if I'd presented a specification rather than a header synopsis. It was a longer list of things that I was expecting, but I was contacted by someone who had come up with an alternate implementation after my presentation at CppCon, Arthur O'Dwyer. Yeah, Arthur. Oh, right, okay. Good chap. His version was based on a buffer constructor of address and length, so it was in fact a span. But it solved many of the concerns of the committee, so we combined our efforts, spruced it up, polished it again. It went to Jacksonville, Mike represented at Jacksonville, and there was more feedback. Everyone was much happier, very positive review. Then it went to GDC. Arthur presented it at GDC. This is the game developer conference that we have every spring. The games community has every spring. We had good feedback, but still not really quite what people wanted. They said, well, we want something that's multi-producer or multi-consumer or... Oh. I now have a multi-producer, multi-consumer ring. I'll be presenting it on Wednesday at our face-to-face meeting that we have scheduled. I'm hoping to finish it before Issaquah. We shall see. I do encourage you to participate, though. It's great putting a paper together, working out all the nooks and crannies, getting the positive feedback and the negative feedback, but the polite feedback, that's the thing. We seem to all be very polite and very good at doing this sort of thing. It's been an illuminating process. I'm going to hand over to Sean now for the rest of the containers.
All right, is everybody able to hear me? Running back? All right. So we're going to talk a little bit about some of the other papers and containers that we've been working on here. I'm Sean Middleditch. I work at Wargaming Seattle, so not too far from here. I'm a lead engineer primarily on the server in Wargaming Seattle. I'm also co-chair of SG14. So I've been kind of pretty heavily involved in some of the organizational stuff going on there, and it's been a lot of fun working with you guys and the rest of the games community, iterating on C++ and the standard. So the first paper that actually I've put out for C++ has actually been the flat containers proposal. So flat containers, they're. I'm so sorry. Is there a way to get the notes bigger? Oh, I got it right here. We're good. Sorry about that. All right, so flat containers are an associative container that, unlike the standard map, is not a node-based container. It is a single contiguous chunk of memory, much like a vector. So the idea here is that it's a little bit more cache-friendly in order to iterate through or find elements in containers of a certain size. These are pretty common in certain certain industries, particularly games, flat containers tend to be pretty common. I've seen very few game engines actually that don't have their own version of a flat container. It's pretty common in certain kinds of managing game objects or certain kinds of managing various bits of physics or AI. It's used all over the place. They're pretty common in other fields as well. Boost has had a flat map, flat set, multi-map, multi-set for some time. Interest in this container has actually been pretty high from a large part of the C++ community. We put out the idea of putting it in there, getting the standard, and we got a pretty large unanimous interest in getting this container in. So one of the benefits of a flat map is that it is an ordered container. So we get a lot of speed from an ordered container. If you have a large number of elements, a hash container is probably going to beat a flat map. Flat map is still a binary search. It's going to be O log n versus O1. However, sometimes you actually do need an ordered container, particularly for using algorithms like set difference, set union, things like this. They don't work with an unordered container. The algorithms just don't even really make sense in some of those contexts. So a flat map can also be very useful if you need an ordered iteration, but you don't want to pay the cost of allocations or the cache unfriendliness of a node-based container. So there is a little bit of open discussion still going on about whether or not we want the flat container to actually be stored in ordered memory or to be stored in a more level ordered format. And the difference here mostly comes down to iteration speed versus the insert and erase speed. So if you have an in-order container, then iterating through it in order is just a simple iteration, incrementing pointers, incrementing offsets into the container, similar to iterating through the elements of a vector. However, the find operations, insert operations, as the container grows, the binary search is jumping around through memory a little bit more. So you tend to lose a little bit of your cache friendliness in this case. You can instead restructure the flat container to be a little bit more friendly to the binary search, so that it is going to be jumping from the first element to the second element to the fourth element and kind of be a little bit more clustered in the beginning of the cache. The downside here is now iteration, you're jumping around a little bit more. So there's some open discussion about what is the ideal use case for a flat container, what sizes are we optimizing for. Yeah, we're still working through some optimization measurements, but it looks like we're probably going to be leaning towards keeping things in order. It's the use case for flat map. If you need a large number of elements, you're probably not using a flat map anyway, and so search speed, searching over a large number of elements isn't really going to be your bottleneck. All right. So now we're going to talk a little bit about the uninitialized memory algorithms. This paper has actually been accepted for C++ 17. So it has been worked on by Brittany Friedman. Is Brittany here? Oh, there she is. All right. So the idea of the uninitialized memory algorithms is that if you're writing a custom container, which is pretty common in some of the high performance areas, games in particular, we have a lot of custom containers. For example, we just went over flat map. Most games have had to write their own flat map. Games have to write their own ring buffers. Lots of different specialized containers for specialized use cases. Writing some of these containers can be a little bit difficult because there has not been so far the library support for some of the internals of how containers are implemented. You allocate memory for a container, you now need to initialize all that memory. These standard algorithms in the library are all based upon manipulating existing ranges of valid objects rather than creating new ranges of valid objects. So for example, the uninitialized memory algorithms add the operations uninitialized copy and uninitialized copy n, which is to copy a range of objects into some uninitialized memory. This would be useful, for example, if you were writing a container like a flat map and you were given a range of iterators of elements that were already sorted. You need to get them into the memory you just allocated for the flat map. Now you have a nice, simple, well-tested and correct library facility to help you write these sorts of containers. So there's also algorithms like fill to take a single value, fill it in to your uninitialized memory. Yeah, we've got the buffer work, which again helps certain containers when doing manipulations. raw storage iterator, which is a nice way to write further abstractions that operate on uninitialized memory when running your own algorithms. And it has been approved for C++17. It is in the working draft of the standard. Unless the committee makes a really weird decision, it's going to be in C++17. So yeah, it's actually one of our first big successes in terms of SG14. So we shall thank Brittany for seeing this through and really helping to improve the standard for everyone. Yeah, so there's a few other weird cases when it comes to initialized memory algorithms and how some of these work. Destroy and the uninitialized move in. A lot of this has to do with dealing with, oh, a little too far. Sorry about that. So a lot of the problems with these kinds of memory algorithms actually comes down to our good friend exceptions. If you have an exception that throws while in the middle of a copy or a move, or when trying to initialize a set of memory, you will have partially initialized memory. So for example, you're trying to copy 10 elements, say you copy 5, an exception is thrown, you now have 5 elements filled in, 5 elements uninitialized. It's not obvious how far you got into this initialization. Dealing with some of these tricky parts is really hard, and a lot of even very experienced C++ developers, myself included in a lot of cases, have not gotten this right in the past. So getting these things into the standard really helps with making sure that the tricky cases with moving, constructing, destructing in ranges with types that might throw is done right and is done in a predictable way that's not going to cause surprises or bugs down the road. It's really useful to have these implemented in a correct way. Another important thing to keep in mind on this is that these are not so much new things. Almost every standard library you've used, or every standard library you've used, has actually implemented these algorithms. This standard library implementers working on vector or some of the other containers that are in the standard library, they need these same utilities. If you look through standard library implementations, you will find that there are copies of these algorithms implemented, just usually in a private, hidden fashion. So this just kind of takes standard practice for library implementations and exposes it to you, the C++ user, so that you can write your own containers. Yep. So this is a lot of what just went over here. All right, so colony and stack is another set of very interesting new containers that are being proposed. So a common use case we run into in games particularly, and many other domains as well, is we need a very large number of objects to be initialized, managed, and maintained. We do not necessarily care about the order of these objects. We don't care how they're sorted. We don't care about looking them up very often. We just need to have some data initialized, ready to go. We're going to iterate over them perhaps every now and again. We're going to add and remove them, but again, we don't care where they're added or removed to. We do, however, need stable references to these objects. We need to be able to grab a pointer to it to know that if we insert another object, it's not going to invalidate all the other pointers we have. So there's a lot of different ways that, a lot of other ways that these sorts of containers have been implemented in the past. A common one is to put, or to use a vector, to know that you're only going to insert at the end of the vector. And if you remove from the vector, that you're then going to use a swap and pop sort of algorithm, and then use indices into the vectors in order to access the objects at a stable position or a stable known location. These themselves can run into problems. If you're using indices, you have to carry references to both the vector and the index, so now you've got these kind of like fat references to the object you're trying to reference. Because otherwise, when the vector grows and resizes, all of your pointers would become invalidated. So colony is an attempt or a very successful version of trying to make sure that we have a container that allows us to push and pop, remove, insert objects that are in a known stable location while being efficient for this purpose. The allocations are meant to be efficient. Iteration through the container is meant to be efficient while giving us these stable locations. And I believe we have a talk coming up on this. Yes. So there is, yep, there you go. So we're gonna have a talk about this. If you are more interested in the specifics of how this the algorithm works. Certainly I can't speak to it with great expertise, but Matthew will be going over that 3:15. So another actual study group is the 2D graphics study group that has been pushed by a number of people in the committee. So this is the idea of having a way of drawing to the screen with 2D primitives. Certainly this isn't the kind of graphics output that is going to be sufficient, for example, with a large 3D game. The Total War series is not going to be drawing things with a 2D output anytime soon. They're using high-end custom 3D rendering primitives or APIs. So this kind of library doesn't seem immediately appropriate to some of the stuff that we've been talking about so far, that we've talked about in previous talks for SG14. However, an important thing to keep in mind is that a very large percentage of games actually are 2D. We get a lot of mobile games, even a lot of desktop games, social games. These games are primarily 2D, and having a good, well-supported, well-documented, community-endorsed way in the language of interacting these is certainly important to the game industry, as obviously well a number of other industries. So this has its own study group working on the graphics. I believe it's renamed to the I/O group now. So they're working on both the output and eventually the input side of this as well. So it's got a lot of the basic primitives you would expect out of 2D rendering if you've done 2D rendering in the past. It's made to really solve an actual problem and kind of be a complete solution in terms of the 2D drawing needs that a lot of us have. So it is very much working towards solving real problems. Now, that said, there are some potential problems with the current proposal in there that some of us in the games industry are a little worried about. So one of the problems with the current proposals is that it is a stateful-based graphics API. So the stateful APIs is the idea of you tell the API, I want to use the red color now. And then later on, you'll tell, okay, draw this shape. And it will remember the fact that you told it to draw red, so when it draws a shape, it draws a red shape, which seems very easy. That's actually the way a lot of libraries have been built in the past, including the HTML5 canvas library, to my recollection. However, this has some problems both in terms of API design and performance. So if you look at, for example, Vulkan versus OpenGL. Vulkan is the new standard by Khronos that is a low-level, direct, faster, more concurrency-friendly graphics API, whereas OpenGL is the well-known, venerable, very stateful graphics API that has existed since 1991, if I recall. So looking at some of the differences in performance between Vulkan and OpenGL, we find that the stateful nature of OpenGL has actually been a problem. It requires a lot more driver code to be written. You can't communicate to the hardware as well because the hardware itself is in fact stateless. It takes small programs, small bits of fully encapsulated state and executes them. The hardware doesn't remember that you set the color to red. The hardware gets a command that says draw this triangle and it's going to be red, essentially. So when you have a stateful API that is layered over this hardware, you have to write a lot more code in order to work around these limitations. You also can run into certain problems in terms of composability. If you say, I want to set the color to red, and then I want to have this helper library I use that's going to go off and maybe calculate a shape for me, what if that helper library accidentally, or not accidentally, but intentionally even sets the color to green for some internal test code or something it has in there, and then you don't know that it was set to green. So now you go to draw your shape that the helper library generated, and it comes out green instead of red. This is a pain. So you end up having to then use a state stack. You have to say, I take my state where it's going to be red, save that state, do this work, restore the state. It's just more performance problems and more room for errors and bugs, and it's just a pain. It's not composable. So with a stateful library, we lose speed and we lose composability. Whereas with a stateless library, where you say, draw this shape and it should be red when I draw it, you end up having a very composable interface. It's faster. There are existing implementations of libraries like this. Pretty much all the users of libraries that were stateful have switched to a stateless type library. For example, replacing Cairo with Mozilla's Azure library. And then there's also some future work needs to be done on the input side of things. There's a lot of different ways this can be done. Certainly modeling off industry practice like Boost or Qt is an approach. I do not believe that the group working on this has quite yet made a significant proposal in terms of I/O, but they are working towards it and coming along. And now I'll hand this off to Michael.
Thanks. Okay, thanks everybody. I always learn so much whenever I listen to these two guys, even because I'm not actually in the games industry. I'm actually in the business of the heterogeneous devices and programming them using a software model for things like neural networks, machine visions, and self-driving cars. So I can't believe the stuff that I'm learning from these guys. So one of the things that I wanted to point out. Does this work? Okay, great. So some of you guys are asking what it means for the Wednesday's meeting. I put together a bit of an agenda as well in terms of the times and some of the proposals that are going to be reviewed in details. We're going to be talking about fixed points. We're going to talk about ring span. We're going to talk about hazard pointers, RCU. So these are mostly, so this is an official SG14 meeting, meaning that it's going to be pretty dry if you're not interested in looking at interfaces, looking at code, giving comments back. But it turns out a lot of you guys actually want to do these things. So I'm pretty happy about that. So for the rest of this, I want to just talk quickly about where we are. You guys already kind of know from beyond this keynote, we are at C++17 review, the committee draft. 3 or 4 things made it, the special map, the file system, the library fundamentals 1, and parallelism 1. Okay. All the other things are still in flight because they were just deemed not to be mature enough. For us, though, I want to talk a little bit about, so SG14 it cares about the little things like an initialized algorithm, thank you, Brittany. We care about the big things like ring spans, flat map, but we also have the big picture in mind, thinking about what it means to reduce, enhance C++ for heterogeneous, to support heterogeneous devices. What it means to support it for concurrency, for further forms of concurrency. So that's why we cross over with a lot of other groups. So this one slide kind of gives you an idea of some of the things that's been accepted. The red is the only thing that was accepted for 17. The blue stuff are what's in flight right now. Okay, and some of that definitely crosses over to the interest of the games community, the financial trading community, as well as the embedded community. Okay. Now, executors, there is a talk coming up Tuesday by my colleague at CodePlay, Gordon Brown, as well as me, on what executors will look like. Okay, because we've been holding a constant every 2-week meeting with all the authors of executors. Right now, there were 3 or 4 proposals that's been deadlocked for about 3 years. But I'm happy to let you know that we do have something that looks kind of like this diagram that is a minimal executor design that bifurcates out what it means to have an execution resource, what it means to have execution platforms, what it means to be an executor. Okay? If you're interested, come to that talk and I'm going to give you a little more information about that. The reason I'm interested in that is because that's important for heterogeneous computing. We need to know how the executors interface between the diverse control structures that we have at the bottom, like async, like for each, coroutines, like infer, and how it would access the various different resources, like a bunch of threads, a bunch of GPUs, some OpenMP runtime, for instance, OpenCL runtimes, whatever that you might be running it under. Okay? You definitely don't want an end-to-end relationship between every one of these diverse constructs to all of those different resources. And that's the kind of the direction we would have been heading if we don't have something in between. Executors is kind of like the marriage between algorithms and containers that we have in terms of iterators. Okay? I'm going a little bit fast because I want to talk a little bit about concurrency toolkit that's also coming up. There's a talk coming up with my colleagues, Maggot Michael, who is absolutely the worldwide expert on concurrency. He invented hazard pointers, as well as my other colleague from my former workplace at IBM, Paul McKinney, who's going to talk about the interface. We're going to show what the interface now looks like, a C++ interface for hazard pointers and RCU. Okay? And a hazard pointer is going to have various operations for allocating, for acquiring or ownership, for setting or reading or clearing the value. But most important, it's also about how to reclaiming the resource. So I don't want to go through too much because I am running out of time. So come to that talk. I think it's on Fridays. Okay. And we're trying to pair it together with this idea that supports this concept of a Schrödinger zoo, where there's a bunch of, okay, the idea is that it's a construct, an in-memory database for the animals in Schrödinger zoo, and that it would record the births and results in the deaths as a deletion, okay? And what happens is there would be queries that would be available, and these would be concurrent. Now, it turns out that there's a lot of queries about the lifetime of the cat, probably mostly from the mice. So if you want to hear more about that particular story, we're going to talk about that on Friday, and how you can do all these things concurrently, okay? And this is a picture of Heisenberg's uncertainty principle, where you have Schrödinger's cat. You can see he's half dead and half alive at the same time. Okay. Other things, vector SIMD. This is going to be this is most likely going to be in Parallelism 2, okay? And part of the thing is we don't have any standard, but we've been reinventing this over and over again. We've had Boost SIMD, but right now we have two proposals going on. Unfortunately, both the name is kind of like Matthias. One is Matthias going on, and the other one's Matthias Kretz. It makes it a little bit confusing, but they managed to come together so that at the end, we kind of usually when these things happen, we do what's called a shotgun marriage and force them to try to come together. This is like a little bit of the South and the West, I guess. So the interface is coming to very nicely. You've heard of this term now. It's called data path. Okay, that gives you the number and the size. Okay, and I'm being indicated I'm going to be cutting out soon. So I want to let you leave this on the slide so you can see what it looks like. Okay. A couple of other things that I want to go over, the final things I want to go over, things like heterogeneous computing. We've been talking about that. I've been looking at four very big candidates. SYCL is one of the is a programming model for heterogeneous computing that's strictly for C++. I've also been, and it's now just recently released as a community edition. I've been looking at LSU's Stellar's HPX for distributed computing, a very nice way of doing asynchronous computing, very thorough, very well supported. NVIDIA's agency for bulk dispatch, these are all very, very good. Okay.
Can you turn your lab on, please?
I'm sorry?
I think your lavalier mic got turned off. Can you turn that?
Okay, thank you. All right. So other things like asynchronous and distributed parallelism API in HPX that I've already mentioned that, as well as heterogeneous computing compiler from HSA. Okay, these are the next big frontiers that we want to talk about, and part of that will be covered on Tuesday's talk on heterogeneous computing. This is about massive parallel dispatch. We talked about the fact that C++, in order to be efficient, this is the age we're coming to. We want to keep it moving in that direction. Okay. I think I'm going to close with one more. I think I'm getting close to the end. I want to close with one thing. We spent a lot of this summer connecting with the financial people. The gamers kicked us off for this particular group, but there's also interest from the financial trading group, and over the summer, these are the kind of things that they've asked us to look at things like massive parallel dispatch on heterogeneous devices. Things like CPU cache memory affinity, as well as high bandwidth memory. Yes, we're looking at trying to make C++ support things like that. This is one of the number one things that the high frequency traders, as well as the financial people, are looking at. Composable memory allocation, something that I think Andre talked about in a couple of keynotes before, as well as exception handling light. We're not shirking away from big things. Patrice has been leading some of that effort, and we've been talking about ways of giving you something, not to remove exception handling, but give you something that gives you lightweight exception handling. If you didn't know, it's already sneaking into C++17 because the parallel algorithm right now, when it has an exception, it actually terminates and does not unwind. So it already is sneaking into C++. All right. Other things that the financial people are interested in, I'll comment some of the things. We're going to be talking about intrusive containers on Wednesday during the SG14 review. There's work on hot set that's going on right now. Okay, and I've already talked about how executors is heading up that same direction. I think with that, I want to close with asking you guys about joining the group and what we plan to do. We plan to continue the direction we're heading with, pushing proposals through. Some of it will make it in through various different iterations, through various TSs. We're going to try to make a big push for embedded computing. That group joined us, and we're beginning to, and one of our mandates is certainly to cover things like low constrained resources in a real-time environment, as well as how to do high performance in a low latency environment. So that's certainly something that we're going to be looking at. And with that, I'm hoping that you guys join us and participate in the group. Many of you guys do. One of the reasons we get so many people is because during these talks, we're talking about what you've done, not so much as what we've done. So thank you very much for coming. Questions? Yeah. Yeah. Absolutely. The presentation will, all presentations, I believe, will be available. So, yeah. Other questions over there?
Joining SG14, is it just a case of joining the mailing list?
Right. So unlike joining the C++ standard requires you to company and countries to send you, SG14, like all SGs, are free to join. Now, it's easy to join SG14. Just Google ISO-CPP space SG14, and you'll find the mailing list. You listen to it. It's really open. This is actually normal for all SGs. Almost anyone is allowed to join, even if you're not a regular standard committee member, because that's the point, is that we want to solicit everybody's feedbacks. Okay? Other questions over here? Yeah.
Why do the parallel algorithms have weird exceptions?
Why do they have weird exceptions? They originally was going to have these things called exception lists, which would have created an exception list of exception lists if there's a complicated nested parallel situation. We realized that was a mistake. Yes, we make mistakes all the time, and we pulled it out at the last moment, at the last day in the Finland meeting, and replaced it with a simple system where you just terminate and don't unwind, with the promise that we might replace it with a slightly more advanced system, like maybe exception through reduction operations, okay, in future. Now, doing it this way means that we can add on top of it. But once we have mandated the more complicated system, it would be very difficult to reduce it back down. Okay, back there, Fichelle.
Yeah, I was wondering, part of it is like compile time exception handling. If you add that into the standard where you can actually declare, whether you have compile time exception handling, and you basically take out the exception handling mechanism if you don't need it. Is that still being discussed, or?
So the question, I believe, is the compile time exception handling mechanism still being discussed? Okay, I think it is, but I don't have much to say about it at this point, unfortunately. Okay, other questions? Okay, well, thank you very much, everybody.